Hello, my name is Roger Watson. I'm from the United Kingdom and I'm currently the Editor-in-Chief of Nurse Education in Practice. Welcome to this session on instrument development and psychometric validation. In this session, we're going to cover three main headings: questionnaire design, questionnaire validation, and also we're going to take a look at screening questionnaires. Under questionnaire validation, we're going to be primarily concerned with content validation, and under screening questionnaires, we're going to look at the concept of receiver operating characteristics and predictive values. I want to include screening questionnaires here because, while strictly speaking, the way that they are evaluated may not come under psychometric validation. They're very useful, often overlooked, and not often covered in any detail in textbooks looking at instrument development and psychometric validation. So I want to include them here just for completeness. But first of all, we'll take a look at questionnaire design. Questionnaire design, as the diagram is supposed to illustrate, is done to develop questionnaires that will be able to find differences between people. And to do that, they must be designed properly. There are two main questions that you need to ask yourself when you are designing a questionnaire. One of them is very obvious and one of them is often overlooked. The first question is, what do you want to find out? That may seem very obvious, but you do need to keep this uppermost in your mind, almost as a research question. It needs to be there to keep you on track, to prevent your questionnaire from asking about irrelevant information, but also to make sure that you do include all the information that you might require. The second question is, how will you analyze the data? As I say, this is often overlooked, and I think it needs to be kept uppermost in your mind right at the beginning of the process of developing a questionnaire. Because if you work back from how you will analyze the data, you can work right back to the kind of questions that you need to include in your questionnaire. So, for example, just to use a simple example, if you wanted to find out the difference between, say, men and women, you need to include a questionnaire that asks that unambiguously in order to enable you, for example, to do a bivariate analysis, for example, a t-test. On the other hand, if you wanted to find out how something changed with age, you need to do that using correlation or some similar process of statistical analysis. Therefore, you need to include a question on age that will provide the data that will enable you to do that. So I just reiterate, when you're designing a questionnaire, in addition to being very clear what it is you want to find out, you should right from the start be very clear about how you will analyze the data. So have that in your mind and design the questionnaire deliberately to achieve that. Don't design a questionnaire and send it out and then have it returned to you and then think how you might analyze the data, because you may find out that you've designed your questionnaire in such a way that the analysis that you propose is not possible. The concepts of authenticity and directness are important Now, authenticity and directness are not often applied in psychometrics. They actually apply to educational tests, and they refer to the extent, authenticity that is, to which you include all the concepts that need to be there to test a student properly, and directness, which means that you do not include irrelevant things which will distract them and which will not give you information about their, for example, their level of knowledge. So authenticity and directness cannot be measured directly, but they can be kept in mind as you're designing a questionnaire. And I think they're very useful in designing questionnaires because it helps you to stick to the point in the questions and not to ask irrelevant questions, but also to have some idea if you do have all the right questions there. I'm not going to talk very much about the process of generating items. That's slightly outside of today's talk or today's session, but if we keep authenticity and directness uppermost in our minds, we'll get the balance between the length and the utility of your questionnaire. These will help you to get this right. Essentially, questionnaires shouldn't be too long. You should always strive to make them as short as possible, and that will increase their utility. A questionnaire is no use if people will not answer the questions. So if you need to ask something, if you're sure that you need to ask, make sure that you do ask it. And if you don't need to ask it, don't. This is easier said than done, but that's the sort of slogans that you should keep in your mind as you're developing questions and adding them to your questionnaire. Try to avoid the just one more question trap. And I can give you a very practical example of the one more question trap. I was involved in a major funded study in the United Kingdom several years ago called the DEM Care Project, the Dementia Care Project. And this had various aspects concerned with it around home care, community care, and other aspects of dementia care. It was a multi-million-pound study funded by our National Institute for Health Research. In the process of designing the questionnaires for it, there were several. Someone said we should ask the people about medication. And the people were either people with dementia who were able to answer the questionnaires or relatives. And there was some resistance to this because we weren't sure how useful it might be, but the person was very vocal and very powerful, and they had their way, and a question about what medication are you currently taking was added to one of the questionnaires about dementia care at home. And it created a complete mess because we gave people no guidance about how to answer that question. So some people gave us the name of a drug, some people gave us the proprietary name, some gave us the pharmacological name, not always necessarily the same preparations, of course. Some people gave the dosages, the times per day, other people didn't. The data, which was collected from tens of thousands of people, turned out to be absolutely useless and a waste of time, and took up months of the time of several pharmacists to try and work out if it was any use before the data had to be ditched completely. So that's a very graphic and very expensive illustration of the just one more question trap. You must avoid it at all costs. If you are responsible for developing a questionnaire, if it's your research project, then you need to take the lead on that. So a lot of this is around leadership as well as all the other aspects of developing a questionnaire to do with psychometrics. Most items will be obvious and will come early when you're developing questionnaires. But question, therefore, every additional item that comes late. Beware of your response formats to questionnaires. This might seem a fairly superficial thing. However, if you have the best will in the world and the best research question, and also the best people around you, and you think you've got all the questions you need and the content's correct. If the questionnaire is impossible to read or impossible to answer, you will have completely wasted your time. So make sure that the questionnaire is designed nicely and that the response formats are unambiguous. So points to consider: have you included all the possible options where options are provided? Have you provided a balanced spread of choices where choices such as opinions are to be selected? For example, you've got to make sure that if you've got, for example, strongly disagree at one end of a Likert scale, you must have strongly agree at the other end. Otherwise, you will bias the questionnaire. Are the options mutually exclusive? Be careful, and I've had experience of this myself, of not having strongly agree at both ends of the questionnaire. Read it carefully and make sure that you haven't cut and pasted the wrong thing. And then, should you provide a neutral or a midpoint response in a Likert scale? There's no clear answer to this. It's really a matter of preference. However, if you don't provide a midpoint, there is some evidence to suggest that people may not respond to the questionnaire. If you're forcing them to make a choice, they may not want to make it. On the other hand, with a neutral response, I've seen myself people just going down the middle point of all the questions. So there's no hard and fast rule about this. I tend to prefer having a neutral midpoint response, but others don't. And I think you've really got to discuss this with your team and think about what the things in favour of that are and what the things against it might be. We're all familiar with the traditional Likert scale. They can be shorter or longer, but the most common Likert scale is a 5-point. This one's about job satisfaction. The questions are nice and clear. They're not asking more than one thing. There's a nice balance of responses from strongly disagree over to strongly agree. And this one happens as I tend to favour to use a neutral point. But do make sure that you lay out a Likert scale nice and clearly like that. Again, you can have the best idea for a questionnaire, the best team, the best content, the best questions, but if you don't provide them to your respondents in a format that's clear, whether it's hard copy or online, then you will not have people buying into your project and responding to your questionnaire. Now here's something that's interesting. These are the demographic aspects. Now most of the questions here are perfectly good. Gender, good. Male or female, of course you may want to add other genders now. Age, and I always prefer that it's specified because it makes it more powerful statistically. I will skip educational qualifications for a second. Years of experience, current post is, first sector, third job, nature of current employment, again, unambiguous. However, educational qualifications written in this way is an example of a very bad question because people never respond to this properly or in a way that is very useful to you. So some people may put Bachelor of Nursing, some people may put first degree, some people may put school level, some may put a PhD, others may put a DPhil. In my country, in the UK, an MA can be an undergraduate degree or a postgraduate degree, for example. It really doesn't tell you very much. And of course, being from a nursing background, we also have a plethora of other certificates and qualifications. So I think a better way to ask about educational qualifications is to put For example, you can assume if it's professionals, they have school education. You don't need to ask that, but it might be worth putting an undergraduate degree, postgraduate degree, and doctoral degree, for example, and just to have them tick those off, or first degree, second degree, third degree, something like that, something which anyone can respond to which they will understand, and from which you can make sense of the data. And the presentation is important. If you're going to ask somebody what they think about something, that's a good way to put it. Nice black and white font, nice and large. Don't try to do anything like this, which is almost impossible to read, or this, which again is very difficult to read. So keep things plain and keep them simple. Next, I want to look at some aspects of questionnaire validation. I'd like to recommend to you an excellent article from the Journal of Clinical Nursing, which was published quite a long time ago in 2009, called Reliability and Validity in a Nutshell. And you'll see that I am the second author on this, and Katrina Bannigan was one of my PhD students, an allied health professional, not a nurse as it happens, and she was developing questionnaires in her own work and ran into the concepts of reliability and validity and tried to get to the root of them, and kept finding, as I had also found years before, that you will find as many definitions, particularly of some aspects of validity, as you will find textbooks. Not everyone describes them in the same way. Now, there is some convergence these days and a much better agreement on what reliability and validity mean, but this article has been very widely read and highly cited, and I think is a very useful look at the concepts of reliability and validity, so I recommend it to you. You will easily find it via Google or by searching the Journal of Clinical Nursing. First, some definitions. Reliability is the extent to which an instrument provides the same measure each time it is used. So in target A, we've got poor validity. Validity is represented by the center of the target, but good reliability. In other words, all the shots are being fired in the same place. And that's an important thing to remember, that something can be reliable without being valid. For example, a ruler can make the same measurement each time you use it, but the ruler may not be calibrated properly. At the other end, the third target represents a questionnaire with good validity and good reliability. All the shots are in the same place and they're all in the center of the target. Whereas the other target in the middle, target B, has got both poor validity and poor reliability. Now, I have seen versions of this with 4 targets, one showing good validity and poor reliability, but that is actually philosophically impossible. You cannot have validity without reliability, but it's quite possible, as illustrated here, particularly in target A, to have it the other way around. We can use exactly the same targets to represent validity. First of all, the definition of validity is the extent to which an instrument measures what it is supposed to measure. So we already know that there's only one valid target here, and that's the one on the right, which has got good validity and good reliability. Just to reiterate, it's valid because it hits the target, it hits what you're meant to hit. The analogy being that a questionnaire measures what it's meant to measure, and it's reliable because it gives the same measure each time it's used. All the shots are in the same place. So establishing validity, well, the ultimate validity, and often it's an overused term, is construct validity. That's what you're trying to obtain, or that's what you're trying to measure and what you're trying to develop in a questionnaire. However, it's worth noting at this point that construct validity is in fact unobtainable. So construct validity is defined. I am a great believer in Wikipedia. Construct validity is defined as the degree to which a test measures what it claims or purports to be measuring. So in the classical model of test validity, construct validity is one of three main types of evidence alongside content validity and criterion validity, but they can be measured. So construct validity is slightly different. It can't really be attained. Some people describe it as the sum total of everything we know about a questionnaire. So modern validity theory defines construct validity as the overarching concern of validity research, and it subsumes all other types of validity evidence. So things like content and criterion, which we will come back to, are contributing to construct validity. But because we can never develop the perfect questionnaire or measure anything perfectly, particularly when it comes to psychometrics and latent traits or hidden traits, we can never really achieve construct validity. I just wanted to, again, return to the point I made. I'm a great believer in Wikipedia. I know that occasionally it gets biographies wrong, particularly about celebrities. However, on methodologies, it's particularly good. And you don't have to cite the Wikipedia page like I've done here. What you can do is you can look in the references that are given and find good references there. So it's very useful. And the common ones on common concepts like validity, in fact the whole of psychometrics, you'll find are updated regularly by experts. So we're going to have a look at some of the types of validity. We're going to look at content-related validity or content validity, and under that we've got face validity. I'm not going to consider face validity in any detail here. Face validity, as you may well know, cannot be measured, but face validity is really, does the test appear to test what it aims to test? In other words, does it look right? Does it read right? Does it have, on the face of it, prima facie, you might say, does it seem to be a questionnaire that's measuring the right thing? But face validity is also contributed to by the extent to which people can read the questionnaire and use the questionnaire. So it's a rather vague term. Some psychometricians eschew it, in other words, they ignore it completely, but I still think it's something that we need to consider. Because if you don't get past the face validity of a questionnaire, if you don't get past the initial look at a question, if people don't feel that it's useful or measuring what they're being asked to respond about, then they won't respond to it. So the face validity has got to be right. Otherwise, you won't get to the content validity. So let's have a look more specifically at content validity. Content validity. Again, I want to point you to an excellent article, this time not one that I've co-authored. This is in Research in Nursing and Health. It's by Polite, Beck and Owen, and it is the CVI, the Content Validity Index, which we're going to look at as a way of assessing content validity, an acceptable indicator of content validity, appraisal and recommendations. Now the good thing here, in this article, it gives you the definitions of these terms, of the different kinds of content validity. It also shows you the equations for working them out. It gives you parameters and it shows you a worked example. I'm going to use some of that here. Content validity falls under several types. Item validity and scale validity. Item validity looks at individual items, scale looks at the overall performance of the scale. And there's also a concept called the content validity ratio, which I'm going to include here for completeness. but honestly, I have never seen this used in practice. The item validity is described as I/CVI, and the scale validity is described as S/CVI. So from this article by Rodriguez, Adachi, and Beattie and McDermott from the BMC Musculoskeletal Disorders, which is a good article, fairly recent, on content validity. We'll look first of all at the content validity index of items, or the I/CVI. So the I/CVI is computed as the number of experts giving a rating of very relevant for each item divided by the total number of experts. It's quite simple. And values range from 0 to 1, where an I/CVI of greater than 0.79 means the item is relevant. Between 0.7 and 0.79, the item probably needs revision. And if the value is below 7, then the item is eliminated. Now, these are arbitrary settings, but they're the ones that are sort of acceptable to the psychometric community. Now, here we have a fictitious worked example from the paper in Research in Nursing Health to which I just referred you. And it's an example using 10 items with 3 experts. Normally you would want more experts. And they are all asked to indicate their agreement with items being relevant on a 3 or a 4-point relevance scale. It doesn't really matter. All we're concerned with are the ones where the experts agree that these items are strongly relevant. So you can look at the proportion of the items, the proportion of the experts that agree. Then you can look at the experts in agreement, and you can see for items 1 to 7 that they're in perfect agreement. For the rest, they're not. Then you can calculate the item CVI, and of course it's 1 where the agreement is universal, and below that where it's not. That actually suggests these are not very good items, as we've seen in the previous slide. And you can actually calculate the average item CVI, which is also a way of assessing the overall performance of the scale. So that's actually a measure of scale CVI, and it's called the average CVI. And we'll see that in the next slide, that would indicate an average CVI of 0.9 indicates that this scale is acceptable. However, you can clearly see that there are 3 items there that are below 0.7, which may need to be eliminated. So this is a non-conservative method of measuring the scale validity, and we'll see a different method, an alternative method, in the next slide. Before we move on, I just wanted to say that numbers generated in this way are useful adjuncts to making decisions about items, but you do want to be careful about removing items too readily, as it may indicate or it may lead to some what we call construct underrepresentation. Some items may be crucial, or some concepts may be crucial, and the fact that the experts haven't agreed with them may not just indicate that the concept is not necessary. You may not have expressed it properly and therefore not asked them properly. So you do need to be careful and achieve a balance. However, the numbers do give you a useful insight. And as I say, you'd probably use more than 3 experts. So the content validity of the scale, it's very similarly calculated using the total numbers of items rated as very relevant, but there are 2 ways of doing this, and they're done in slightly different ways. The universal agreement amongst experts is the least conservative way and probably the preferable way. And here you add up all the items with an I/CVI equal to 1 and divide that by the total number of items. So in other words, you don't use all the items, you only use the items that are universally agreed with, and then the indication of excellent content validity is over 0.8. But there's also the average CVI, which we saw in the previous one, and this is less conservative, and it's taken by calculating the sum of all the I/CVIs, not just the ones that are universally agreed with, dividing by the total number, and an average of over 0.9 there is usually considered to indicate excellent content validity, but that is, as it points out, they are less conservative than the universal agreement. I don't have any strong, clear advice as to which you should use. I think it may be a matter of preference or what you want to achieve or how important it is, but it may be better to veer towards the universal agreement. However, you've got to beware that the more stringent you are, the less items you will have in your questionnaire. So as I say, it's a balance. I wouldn't be driven by these numbers, but I would try to work to get them as high as possible and to report them and to, as I say, use them as an adjunct to other decisions about the items that should be included in your questionnaire. And now, just for completeness, the content validity ratio. I have to admit not to having used this myself, but that doesn't mean to say that you couldn't or shouldn't. And I very rarely see it being reported. And I have to say there's not, according to the literature I've looked at, a very strong agreement about what the appropriate level of CVR should be. Nevertheless, let's take a quick look at it. It's computed to specify whether an item is necessary for operating a construct in a set of items or not. An expert panel is asked to give a score of 1 to 3 for each item, ranging from essential, useful but not essential, and not necessary. And then this complicated formula is used on each item. Self-explanatory. And it gives you a range of CVR from -1 to 1, so it's not from 0 to 1. And clearly the higher the CVR, the better. And all I could find online was that one rule of thumb suggests that a CVR of at least 0.78 is necessary to deem an item or a scale as valid. So it can also be used for a whole scale. So I would I'd leave that to you. You can possibly explore that yourself. I don't have enough experience with it to advise. I have to say it seems a little bit unnecessary and perhaps overkill over the key measurement, which is the item CVI, but that's my view. Next, I want to look at criterion validity. And criterion validity encompasses concurrent and predictive validity. I'm just going to look at definitions here and concepts. I'm not going to go into precise, detailed methods of calculating these. Again, from Wikipedia, criterion validity is the extent to which an operationalization of a construct, such as a test, relates to or predicts a theoretical representation of the construct, in other words, the criterion. So the operationalization, a very clumsy word, that just means putting an abstract concept into a measurable form, but you also need to have some idea of how that, of how to know whether that criterion actually exists or not. So it could be a measure of clinical depression, the extent of clinical depression measured through a set of items asking people's happiness with life or tendency to have suicidal ideation, for example. Here's a slightly more exposed version of the diagram I used before to illustrate content validity and in passing face validity. On the right hand side now we've got criterion validity, which I've defined, and I've also shown you that this is composed of concurrent and predictive validity. Concurrent validity means simply, does the measure that you're developing relate to an existing similar measure? So for example, you could measure the extent of depression against quality of life, and you would see if the two measures correlated. Now, I'm not going to go into the specific statistical tests here or the details of the test. That's to do with learning about statistics and SPSS or whatever packages you use. But you would use correlation between the two measures, and if they correlated, then you could assume that there's concurrent validity. You can also use predictive validity. In other words, does the test predict that something will happen later on? So for example, if you're picking up, for example, thoughts about suicidal ideation or unhappiness with life, does that predict a diagnosis later on of depression? And that could be done by, for example, having a later measure of depression, yes or no, or the extent of depression, and relating that back to your measure. So you could do this using correlation, or you could use it using the score and using a cutoff score on the questionnaire and doing a t-test to help you to look back at the groups who were measured first of all to see if their scores did indicate whether they were likely to be depressed or not. Now this takes us very close to the concept of screening questionnaires, which I'm going to come back to later. It's not exactly the same thing, but it's related to that. So that's criterion-related validity. So content and criterion-related validity are both components of the overall concept of construct validity, and criterion-related validity has its own underlying concepts of concurrent and predictive validity. And finally, a look at construct validity. Again, expose further on the bottom left, really the construct validity is about whether a test relates to underlying theoretical concepts. And that's to do with more than just measurement. That's to do with the overall knowledge of what you're trying to measure and the overall contribution that your questionnaire, and indeed other questionnaires and all the tests that you do around that construct do towards helping you understand that construct. Next, I'm going to look at factorial validity. Factorial validity is sometimes mistakenly, by the way, called construct validity or sometimes called structural validity, but what we want to look at here is the actual structure of the questionnaire, and there are two main ways of doing this, and one of these is factorial validity, which, as the name suggests, means using factor analysis to analyze the performance of your questionnaire. So again, I don't want to go into the details here of factor analysis. That's the subject of another session and requires specific knowledge. But I think from the point of view of psychometrics that you need to understand what factor analysis does. So it's always good to start with a definition, and this is a definition of factorial validity. It's a little bit dry, I'm afraid, but it's from Piedmont, 2014. Says that factorial validity examines the extent to which the underlying putative structure of a scale is recoverable in a set of test scores. In other words, putative means that you suspect that there's a structure there, there's a logical or common sense reason for suspecting that. But when you actually run the questionnaire and give it to enough people and analyze the data, do the scores represent that? And factor analysis is a method which specifically helps you to examine that. Here's a diagram which is meant to show you what factor analysis is about. This is a questionnaire, nothing to do really with clinical or work or nursing, but a questionnaire on service dimensions might have three putative dimensions to it: quality of service, value for money, and expertise. And of course, under each of these, you can see that there are different items. For example, quality of service. Do people listen? Are people treated as being important? Is there an accurate service? And is it delivered on time? So it's exactly analogous to items in a questionnaire and the different dimensions of that actual service. Of course, the service dimensions is really the construct that you're trying to measure. So factor analysis is a statistical technique, a correlational technique, which comes from classical test theory, which is helps us to both to examine the extent to which a questionnaire has underlying dimensions and then to establish the veracity of that structure. And towards that end, there are different types of factor analysis. Exploratory factor analysis and confirmatory. Now, the exploratory factor analysis is there to help us establish if there are underlying structures in a questionnaire. You may have a structure in mind. This helps you to explore it, or indeed, it may show you a novel structure. But you cannot use exploratory factor analysis to hypothesize that you've achieved the structure that you had in theory. That can only be done through confirmatory factor analysis. Under exploratory factor analysis, there are several methods: principal axis factoring and maximum likelihood factoring. Principal axis factoring is used quite commonly. It's available on SPSS. And also principal components analysis, which is very commonly used. And that is presented under SPSS as a form of factor analysis. There's an asterisk there. That asterisk is meant to indicate that it's not strictly a form of exploratory factor analysis. I wouldn't worry too much about this. There are differences in the way it uses the correlation matrix, and they're quite important, but in fact, in reality, and I've discussed this with many experts, the outcome is almost, the outcome, say, of principal axis factoring and principal components analysis is almost usually identical. And remember, this is just a way of exploring structures. Really, you've then got to go on to confirm those structures in order to be sure that they're giving you something that that really relates to reality. And confirmatory factor analysis is a way of doing this. You can hypothesize a structure and then test it. And confirmatory factor analysis is only achievable through structural equation modeling, which takes a little bit of expertise to master. So those are the different types of factor analysis. Exploratory and confirmatory, that's the big division. You need to be clear what the strengths of both are and the purposes of both are. Most common method is PCA, or principal components analysis, but you do always need to qualify the use and say it's not strictly exploratory factor analysis, but have confidence if you're using it that it's as good as exploratory factor analysis and usually gives you the same results. It's much easier to use, and actually I think more commonly used. It's most commonly used in nursing. I've demonstrated this in one small project I did, and it's easier to use, and I think it's easier to understand and interpret. As opposed to factor analysis, which comes from classical test theory, I just want to introduce you to another way of looking at the structures of questionnaires, and this is item response theory. Again, I don't want to get into the details of the analysis here, but I do want to at least expose you to the basic ideas. Always good to start with a definition. So item response theory is defined as the item response theory, also known as latent response theory, refers to a family of mathematical models. So here we're looking at several types of ways of analyzing this concept. These all attempt to explain the relationship between latent traits, in other words, what you can't see, and their manifestations, in other words, what you can measure. Put very simply, if I have a 10 item questionnaire about depression, the items can be scored 0 or 1, so 10 is the maximum score, 0 is the minimum score. What does 5 mean? How depressed is somebody if they have a score of 5? Is that score meaningful? And there are various parameters used within item response theory models to tell us how meaningful that number is. So this is different from classical test theory. It's not based on correlation. It's not looking at the structure in the same way, but it's giving us very valuable insight into the performance of questionnaires. And item response theory is much more commonly being used in questionnaire development, and particularly in nursing these days. In item response theory, the unit of analysis is something called the item characteristic curve. And that's what an item characteristic curve looks like. I'll come back to that in the next slide. So the ICCs are also known as item response curves, or IRCs, or item response functions. Means the same thing. Most commonly referred to these days as the item characteristic curve. Now I'm just briefly going to try to explain what the item characteristic curve is here by visualizing it. It's not so easy to talk about these in general terms in the way that you can, for example, about factor analysis. I have to say this is not particularly easy. Don't worry too much if you don't grasp this the first time. But the item characteristic curves look like this. There are two of them here for two items, and I'll come back to why there are two items in a minute. The x-axis, described by theta, is the extent of the latent trait, the actual extent of the latent trait running from low to high, from left to right. That could, for example, let's just go back to my example of depression. So the further to the right you are, then the more depressed you are. The y-axis represents the actual score on the item, or the probability of the latent trait existing based on that score, again going from 0 to 1, from no probability to high probability. And the idea is that the greater the score on the item, or the probability of that score, the greater the extent of the latent trait. That should be obvious in a way, but the latent traits are related by these curves called item characteristic curves, and they always have this characteristic S shape or sigmoidal shape. So having two items here, what does that tell us? Well, item 2 is more difficult than item 1. In other words, item 2 represents more of the latent trait. It's further over to the right. It represents more of the latent variable. And more difficult items will have lower mean scores on the latent variable. In other words, the easier an item is, the more likely it is to score high. Again, using the example of depression, if you had two items, one saying, for example, I don't feel like getting out of bed, and the other one saying, I have suicidal thoughts, you're much more likely to score high on the lower of those two items about not wanting to get out of bed. That would be item 1, than on the other score. So, in other words, the scores are related to the actual items, and therefore the scores in item characteristic curves and in item response theory actually mean something. Now, not every item in any questionnaire will fit within the parameters of item response theory. So there are various parameters into which I'm not going to go at all, which are used by different models of item response theory to gauge how good an item is. So slightly in contrast to classical test theory like factor analysis, which looks at the performance of the overall group of items, item response theory, you could say, is differentiated by being very concerned with the performance of individual items. Now that's a very quick look at item response theory. Finally, the different methods that can be used for item response theory, essentially 3 of these. Rash analysis, which is considered to be a parametric model, as is the partial credit model, and then a non-parametric model with which I'm most familiar, Mocken scaling. There are different pieces of software for running these. You can run them all on R, which is the public domain software. Finally, to recap, the advantages of item response theory are that only a specific set of items produces a given score on a latent variable. So in other words, not all items will add to that in a sensible way, and there are parameters for working that out. And therefore, you will know what a score means. If I tell you that somebody's got a score on a depression scale of 5, you know exactly what that means, and you know which items are included under that. As I flagged up in the opening PowerPoint, I'm going to consider screening questionnaires now and the parameters by which we can judge how good they are. So first of all, how does a screening questionnaire work? Initially, a score is given to a person on a list of questions, and then a decision has to be made on the basis of that score. For example, if they are going to be fit and well, or if they're going to potentially die. I mean, that's a dramatic example, really. Really, screening questionnaires are usually used to decide if someone has or has not got a particular condition. The point behind screening questionnaires is that they produce a dichotomized answer at a particular score. And of course, what we need to know is whether that score is really meaningful. So why do we use screening questionnaires? We use them to find out if someone has something, a condition, or is likely to have something. For example, depression, problem drinking, an eating disorder, bowel cancer, or medications management risk. Can they or can they not manage their medications? So why use them when an actual diagnosis is available for some of these things, for example, for bowel cancer? Well, there are several reasons. One of these is the speed and volume whereby they can be used. In other words, we can screen many people quickly. I'm sure you'll appreciate that you cannot screen many people definitively, which requires an endoscopy for bowel cancer, an endoscopy and a biopsy. They have the potential to save lives and to prevent morbidity, so we can hopefully tell accurately if someone has a condition and whether they need to be treated, and thereby prevent morbidity and possibly even, for more serious conditions like cancer, prevent mortality. We can also use resources appropriately. It doesn't matter what kind of system within which you work, a heavily socialised system like the United Kingdom with its National Health Service, or within a system that uses more private medicine or insurance-based medicine. It really doesn't matter. Healthcare costs money and it uses resources, and we have to use those as appropriately as we possibly can. So we need to try to focus our expensive investigations, for example endoscopy, on the people we think are most likely to have the condition, and we try to confirm that, and we try not to waste resources on people who don't. It does come down ultimately to the use of resources, in other words, money. So we can investigate or intervene only when necessary, and alternatively when the procedures are dangerous. And again, I'll use the example of endoscopy, colonoscopy, for example. It's a dangerous procedure. It can lead to perforation of the bowel in some cases. So we reduce the risk of those dangers, particularly to people, from people who don't need the procedure. We only focus them on the people who do. But of course, we have a problem, and it's at one level a mathematical problem, and at another level it's a philosophical problem. How do we decide what the questionnaire is telling us? We need to attach a score on the questionnaire to the level of risk or the probability of that diagnosis. That's the art really, and the science of screening questionnaires. Problems. Sometimes the questionnaire will be wrong. We know, for example, we'll be very familiar at the time I'm putting this lecture together with the COVID pandemic and the tests for COVID. There are two sets of tests. One is the PCR, the polymerase catalyzed reaction test, and the other is the lateral flow test. These two tests work in very different ways, but that's not the point of what I'm trying to convey here. They work in different ways because the PCR tests are highly sensitive, but not very specific. In other words, they produce many what are called false positives. I'll come to these in a few slides' time. In other words, they often pick up and indicate that someone has COVID when they don't. On the other hand, the lateral flow tests are very specific because they're immunoassays, but they are not very sensitive, so they are likely to do the opposite. They're likely to indicate that you don't have COVID when you possibly do. On the other hand, if you feel you have COVID, have the symptoms, and a lateral flow test positive, you're very likely to be suffering from COVID. So sometimes we've got to accept that a questionnaire will be wrong. There is not a perfect screening instrument anywhere in the world. And of course, what this means that sometimes we will put people at risk by missing out on a diagnosis. Other times we will waste resources by using them inappropriately. So some people will be at risk and screened as okay, but some people not at risk will be screened as not okay. What I want to do here is to look at a bowel cancer screening instrument. It's a fictitious one, but it's not dissimilar to the sort of instruments that might be used. So it asks the following questions. 1, do you have bloating? Do you have pain? Do you have a changed bowel habit? And do you have blood in your stool? So let's just go over each of these in turn. Bloating can be a sign of bowel cancer, but of course alone it's possibly not. There are many things that can lead to bloating. Pain, of course, can be an indication, but of course we can have abdominal pain for other reasons. Changes in bowel habit, in some ways almost a cardinal sign sometimes of bowel cancer being present, but of course there are many things that can lead to changed bowel habits. And blood in the stool, again, often a very clear sign of bowel cancer, but of course this can be caused by many other things like hemorrhoids and diverticulitis. So put these things together though, and if someone scores highly on this, it is quite likely that they do have bowel cancer and certainly merit further screening by endoscopy. So there's a simple questionnaire which could be used, but score ranges from 0 to 4. How do we decide if someone's at risk of bowel cancer? Do we decide at 1? Very unlikely that we do that. Do we decide at 2? Maybe 3, that's getting more likely, or do they have to score all 4? And you can see a couple of problems here. One, of course, is that each of these may not be weighted the same way. They may not necessarily each be worth the same score, but that's another issue. Weighting of questionnaires is not something I want to get into here. It's not usually necessary, but you can see a problem with all of these. If you made it highly sensitive and used a score of 1, you'd waste an incredible amount of resources doing endoscopies. At 2 and 3, you would be doing better possibly. 3 probably better than 2, but are you missing people at 2? If you wanted to be Not absolutely sure, you can't be absolutely sure, but if you wanted to be more sure and make this much more specific, then you could use a score of 4, but of course you risk missing out people who are at risk. So there's a decision to be made, and of course the way to do this is to look at the performance of the questionnaire next to a definitive diagnosis. And you do need a definitive diagnosis in order to be able to gauge how well a screening questionnaire is working. So the basic problem with a screening questionnaire is really, at what score do you decide there's a risk? And that score, of course, may not just be clinical, it may also be based on resources. So in different contexts, different scores may well be used. So how do we make decisions about how well a screening questionnaire is working? I'm going to use this diagram several times here. To some extent, I apologize for that. And I'm going to use slightly different versions of it. I couldn't find one that was completely suitable to demonstrate this all the way through the presentation. But essentially, these are we're going to look at what I would call true positives for a start. And on this table, which is a 2x2 contingency table, we've got all the potential, all the possible outcomes of testing. There are no alternatives to this testing. Let me see if I can use a, yes. So for example, along here you've got the true condition. In other words, this is the diagnosis. The person has the condition and the person doesn't have the condition. Down on the left-hand side, we have the test outcome. The test outcome indicates that it's positive or it indicates that it's negative. Of course, we don't know until we run the actual diagnosis at the top. There are only 4 possible outcomes. There's true positive when both of these come together, the test is positive and the diagnosis is positive, and there are true negatives where the test indicates negative and the diagnosis is indeed negative. However, there are also conditions where the test can be negative and the condition can actually be present. That's called a false negative. And concomitantly, where the test is positive but actually the condition isn't present, you can have a false positive. These are called type 1 and type 2 errors respectively. Don't worry too much about that. So if the condition is positive and the test outcome is positive, you get a true positive. On the other hand, if the test is positive and if the test is negative and the condition is positive, you get a false negative. If the condition is negative and the test is indicated negative, you get a true negative. And the false positives are where the condition is actually negative, but the outcome indicates positive. So we can use the numbers of people falling into these different categories to work out how well the test is actually working. Here's a simpler version of that diagram, and I'm going to return to this a few times in the following PowerPoints. And again, it shows exactly the same information as the previous slide, except by convention, it labels the boxes A, B, C, and D. A for true positive, B for false positive, C for false negative, and D for true negative. And those numbers can be used to work out various parameters. So when you see the equations in the following slide, you'll know what those numbers mean. But don't worry too much about these equations. I can almost never remember them myself. I always have to refer to them if I'm going to do any calculations or indeed teaching about this. So don't try and memorize these. I just want to show you that it's possible to work out a range of parameters from those four numbers that appear in those different boxes. So here are 4 equations for the 4 parameters that we can use to judge how well a test is working. And respectively, these are the sensitivity and the specificity, which I've referred to already. And these can be worked out using cell A divided by cell A plus C, and you can multiply that by 100 to get a percentage. Specificity is cell D divided by cells B plus D times 100. That gives you the specificity. And I will show you these relative to the actual contingency table in the next PowerPoint. We can also work out two values, which we'll come to later in the presentation, called the positive predictive value, the PPV, and the negative predictive value. And I will come back to what these mean later. But again, you can see from the numbers, from the equations, that these can be worked out in a very similar way. None of these equations are the same, by the way. They're all slightly different. So using those, we can see that which columns, the true positives and the false negatives, A and C, are used to work out the sensitivity of the test, and B and D are used to work out the specificity. A and B are used to work out the positive predictive value, and C and D are used to work out the negative predictive value. If you're wondering why you need all these particular parameters, sensitivity and specificity tell you how well the screening tool is working next to a gold standard or test, and the predictive values tell you, if they do score on the positive side, how likely they actually are to have the condition. So they work from the actual results of the screening test. So they give you slightly different values and or slightly different insights into the performance of the questionnaire. Put simply, sensitivity and specificity are probably more useful to the researcher, but they're very important in actually helping to set the parameters for the test. And the PPV and the NPV, the predictive values, these are probably of more use to the clinician. So sensitivity and specificity, we'll just take a quick look at these, what they mean, how to calculate them, and how they are related to one another, because that's very important in how we understand how screening tests work. Right, here's another ghastly looking box with all these particular parameters in them here. This time, instead of A, B, C, and D, it's using a slightly different way of presenting it. So let's look at the sensitivity for a start. In a medical diagnosis, the test sensitivity is the ability of a test to correctly identify those with the disease. In other words, the true positive rate. So we can work out from the figures here. I'm not going to do the actual calculations. If we use the equation for sensitivity, which uses this particular pair of boxes here, A and C, we can work out that the sensitivity of this test is 0.66. You'll just have to take my word for that. On the other hand, if we look at the specificity, specificity is the ability of the test to correctly identify those without the disease, the true negative rate. So the specificity is calculated using cells B and D. And again, I hope you'll be willing to take my word for this, but that works out at 0.52. You can multiply both of those values by 100 to make 66% and 52% respectively. Really doesn't make any difference. It's just a matter of preference. But what that tells you is the sensitivity is 66% likely to be correct according to the diagnostic test, and the specificity is 52% likely to be correct according to the same test. But the important thing to realize is that sensitivity and specificity are a trade-off between each other. So here's just putting it together. Medical diagnosis, test sensitivity is the ability of a test to correctly identify those who have the disease, whereas the specificity is the converse. It's the ability to test correctly those without the disease, the true negative rate. And this is what it looks like schematically. What lies behind the theory is that people without the disease and people with the disease, lying on either side of this line here, are considered to lie in different statistical distributions. Therefore, you're looking for the likelihood that they will fall within those distributions. So you're looking at you're trying to find out people who are truly negative and truly positive, and you're trying to avoid the false negatives and the false positives. And this line here is the line on the test result, which gives you the best result. And the problem is that you can never entirely separate these two. The distributions always overlap. It is impossible to get a test which has no false negatives and no false positives. We can work to find the level at which these are minimized. So there's essentially a trade-off between sensitivity and specificity. In other words, the bigger one is, the smaller the other is likely to be. If you try to make a test highly sensitive, you lose the specificity, and vice versa. If you try to make the test very specific, you will lose sensitivity. So the more sensitive a test is, the less specific it will be, and the more specific a test is, the less sensitive it will be. And if it's very sensitive, you will increase the number of negative people diagnosed as positive, and conversely, if it's very specific, you will miss more people who are really positive. So this is another way of looking at it in terms of the actual values. On the left-hand side, sensitivity is very high, but of course specificity is low, and on the right-hand side here, specificity is very high and sensitivity is very low. There's never a point at which they're both high. They converge here, but you can see that they are both less than 100%. So we're always working in this region here. We'd never want a test that was here because it would be very insensitive. We'd never want one here because it would be very non-specific. So we're always working around this region here. So how do we decide what is best? How do we decide the point at which a test works best? Well, this is done using something called receiver operating characteristic curves, or ROC curves. I would be most surprised if you haven't heard of these, or at least seen them, or seen the concept in your reading, especially those of you in clinical practice where screening tools are used. So what are receiver operating characteristics? The word receiver comes from the fact that these were used by radio operators, and they were developed during the Second World War, when radio operators had to tell if there were enemy aircraft coming in, and they found that they could either pinpoint exactly where they were but lost other information as to what they were, or vice versa. So it was, you couldn't get a perfect location and a perfect indication of exactly what was coming in. You could get a very, very high indication that there was a flock of geese coming in and pinpoint them accurately, but you wouldn't necessarily know what they were. Whereas if you were less sensitive and went for less specific and went for a more sensitive test, you could see more objects coming your way, like that's doing there, but you were less certain about what they were. So there was always a trade-off between knowing what was there and where it was. So it was first developed by electrical engineers and radar engineers during World War II for detecting enemy objects in battlefields. And again, that comes from my old faithful friend Wikipedia. So just to run over that quickly, the term receiver operating characteristic, also known as ROC, has its roots in World War II, and ROC curves were originally developed by the British as part of what was called the Chain Home radar system, which was there to detect incoming enemy aircraft. The rock analysis was used to analyse radar data to try and differentiate between aircraft and other noise, for example, as I've said, flocks of geese. But they realised that as the sensitivity of the receiver increased, so did the number of false positives. In other words, the specificity went down. You knew something was there, but you were less certain what it was. So the rock curves were used to develop the level at which the sensitivity of the receiver should be set. So the receiver operating characteristic allows us to combine graphically sensitivity and specificity. And it allows us to find the optimal level of sensitivity and specificity. And this is what a receiver operating characteristic curve looks like. It plots the sensitivity against 1 minus the specificity. You can't plot sensitivity against specificity. You need to use the 1 minus in order to get that particular shape of curve. And that's because sensitivity and specificity, of course, are reciprocal. So how is that useful? One of the things we can do with the receiver operating characteristic curve is to have an imaginary line there, the dotted line at 45 degrees on the graph. And if the blue line, if the curve actually was at 45 degrees, we could work out that this is no better than guessing. Your test is no better than having a look at someone and guessing whether they're depressed or have bowel cancer. However, if the curve lies above that and the area lies above that, and it's the area that we use to determine how well the test works, then we know that this is better than guessing. Of course, we need to decide at what level it is better than guessing to make sure that the test is useful. On the other hand, if the line falls below that dotted line, if the curve actually falls below that, we're actually worse than guessing. We're actually making entirely the wrong decisions. And in fact, it's the area under the curve that we used to indicate whether the receiver operating characteristic curve is acceptable, and we usually use an area under the curve of 0.7 as the very minimum area under the curve that we can use to indicate that a test is good. We usually want it to be bigger than that. What I'd like to do now is use a real example just to show you exactly how this works in practice. So we're going to use a questionnaire, a real questionnaire called PAID, which is the Problem Areas and Diabetes Questionnaire. It's got 20 items on a 5-point scale. Has questions that are, for example, feeling depressed when you think about living with diabetes or so forth. 20 of these questions, from not a problem to a serious problem, 0 for not a problem and 4 for a serious problem. So the scale score can run from 0 up to 80. So at what level do we decide someone has a problem with their living with diabetes? This is what the questionnaire looks like. That's all 20 questions. There's not any need to dwell on that. These are real data from the PAID questionnaire. So what you're looking at here is a plotted receiver operating characteristic curve. The green line indicates no better than guessing. The dotted line is used to tell us where the score should be set. And in this case, there are two figures here. Figure 1 is the ROC curve of the PAID questionnaire score for screening clinical depression. and assuming that the area is greater than 0.7, which it is, we can use that point between 37 and 38. In other words, 37.5 is the score at which you would decide someone probably needed a more definitive diagnosis of depression because they weren't handling their diabetes very well. Figure 2 is for subclinical depression. So the questionnaire can be dichotomized in two different places for two entirely different diagnoses. And here we can see from the dotted line that a score of 34 indicates that someone is likely to be suffering, if they have a score greater than 4, to be suffering from subclinical depression. So that's how the receiver operating characteristic curve works in practice. Of course, you can plot these out with statistical packages, and the statistical package will give you the optimum level at which the questionnaire works for your particular diagnosis against that particular score. And some packages are quite clever, and you can actually move the score about and see the sensitivity and the specificity changing. And you may want to do that because you may, in some cases, want a test that is more sensitive than specific. In other cases, you may not. So these things are not just a mathematical decision, they can also be a policy-based decision. Nevertheless, the receiver operating characteristic curves tell you where the graph is most likely to be correct against the gold standard in diagnosing someone with the condition if they've got it, and not with the condition if they don't have it. So how do we decide the optimum levels of sensitivity and specificity? Well, I've shown you this in a way already. We can draw a 45-degree line, or we can actually calculate it using something called the Uden index. So we don't need to plot out the figures. We can plot the Uden index, which is J equals specificity plus sensitivity minus 1. So we can actually work this out mathematically if we know the specificity and the sensitivity, and that will tell us the point on the curve at which to make our decision. And here's another example. This is not the same example. This is one where everything is shown. The area under the curve, 0.938, so it's clearly a very screening instrument that performs very well. It's got good sensitivity and good specificity. It happens also to have good PPV and PNV, which I'll come to in a few minutes. And that's, if you use the Uden index, that's where you would calculate the dichotomous point to be between indicating that someone has the condition and is worth doing further diagnosis on, or most likely doesn't have it and isn't worth investigating any further. Finally, going to consider sensitivity and specificity versus PPV and NPV. Now, we've done sensitivity and specificity in detail there, and I've already indicated that these sets of values are more useful for different things, and sensitivity and specificity are really for the scientist or the person in the laboratory or the person developing the test to decide where, against the gold standard, it is most likely to be best, or how best it's going to be used to tell you whether someone is or is not likely to have that condition. On the other hand, PPP and NPV are more for the clinician, because they indicate in the real world how likely somebody with a positive test is to have that condition or not to have that condition. So this is an excellent paper by Robert Trevethan, Sensitivity, Specificity and Predictive Values, Foundations, Pliabilities and Pitfalls in Research and Practice from Frontiers in Public Health. This is completely open access, so you can easily find that paper yourself online. And in the paper, Trevethan describes how arguments are made that sensitivity and specificity should be usually applied only in the context of describing a screening instrument's attributes relative to a reference standard, and that predictive values are more appropriate and informative in actual screening contexts. So the positive predictive value versus sensitivity can be described as follows. The positive predictive value definition is similar to the sensitivity of the test, but the two are often confused. However, the positive predictive value is useful for the patient, while the sensitivity is more useful for the physician, because the positive predictive value will tell you the odds of having a disease if you have a positive result. So the sensitivity and specificity will indicate to the researcher or the physician that this is indicating that they're likely to need to be investigated, but then you can tell the patient, but having had a positive value, I can tell you that you're this likely actually to have it or not. And different tests perform differently, therefore the patient may, for example, come to a different decision from the physician and may decide, well, I don't want to proceed with screening. So here's five sets of results which are presented by Trevethan, and they're from real screening instruments. One for shoulder pain, two for peripheral artery disease, one for carpal tunnel syndrome, and one for aspiration following stroke. And it gives you the full range of the values of sensitivity, specificity, PPV, and NPV. And the first thing you can see by looking at that and scanning across it is that these do not necessarily work or move in the same direction. For example, the shoulder pain screening instrument's got very high sensitivity and very low specificity, but the positive predictive value is very low, but the negative predictive value is high. And almost conversely for sensitivity and specificity, the carpal tunnel syndrome test has very low sensitivity and very high specificity, but again has very low positive predictive value and very high negative predictive value. So they don't necessarily move in the same direction. So you cannot assume from a calculation about sensitivity and specificity and the performance on the receiver operating characteristics how that will work in actually predicting from the positive values the likelihood of having that condition. You need to work out all of these parameters in order to understand the test fully. And I have to say that you cannot do without sensitivity and specificity. You need to have those to provide a cutoff point for the test, but there's much more of a move these days towards reporting PPVs and especially and also negative predictive values when people are presenting screening tests. So all I'm saying from that is reiterate, you can't assume, for example, a high positive predictive value from a high sensitivity or vice versa. So in summary, diagnostic or screening questionnaires, they only work when you have a binary outcome, yes or no, does the person have the condition or not. Sensitivity and specificity are antagonistic. Sensitivity and specificity can be combined to find an optimal level of each. That's your receiver operating characteristic curves. And the receiver operating characteristic curves help us to optimize diagnostic and screening questionnaires. But finally, positive and negative predictive values are helpful in real screening situations. This is my email address. If you have any questions or indeed any corrections, you may follow my research at ORCID using that number or scanning the QR code. You're welcome to follow me and interact with me on Twitter. I warn you that my Twitter site is about my own writing other than academic writing on the whole. You may not necessarily agree with me on Twitter. That's fine. but please be polite, and I promise I'll be polite back. And if you use WeChat, you may scan that QR code and you're welcome to interact with me on WeChat. I hope that was useful, and I'd like to thank you very much for listening.